Today we have an episode we've tried to do for a long time. There's some context to that story, which you'll hear in a minute, but we finally had the opportunity to catch up with Brandt Saxey with CoreBrace. If you've done work in the West or in that pocket of the central, slightly east New Madrid fault, then you have definitely spoken to this company and maybe even to Brandt. So let's jump into the details and learn what we can about the BRB system. Also, real quick, our nice recorder cut out for a moment, so we have a few minutes of this episode that are fine audio quality, but not perfect. This is what the bad microphone sounds like. Don't adjust your headphones, it's us. Back to it.
The Structural Engineering Podcast.
Brandt, thank you for joining us today at the NASCC Steel Conference. We're super excited to have you on the podcast. You know, for many of our listeners, probably have absolutely no clue that 6 years ago, we sat down and had the same conversation, and it was one of only 2 episodes ever to be corrupted. And
We've
happy to
better.
make this happen. Yeah.
And I wasn't the corruption. Just
Good clarity. Absolutely.
Well, it's great to do it again, though. I mean, that was a trial run, and we'll be even better this time. So
Yes, absolutely. Well, would you mind giving us a little intro of yourself?
yeah, I'm Brandt Saxey. I'm the technical director and the vice president of Preconstruction Sales at CoreBrace. I've been there about 16 years now, something like that.
Wow.
Prior to being there, I was a practicing structural engineer, and I grew up the son of a civil engineer. My father was a civil engineer who was turned into a contractor by my time I was in high school and graduated and finished his career as a general contractor. So I grew up kind of in the engineering and general contracting world, and so this has been a great fit for me. I was initially kind of led to CoreBrace a lot because of its interesting research and academic position, as well as being a really interesting engineering topic. We had used them at the structural engineering firm I worked at, and so it's been a wonderful career for me.
This episode is sponsored by Idea Statica, software built for structural engineers designing steel connections, anchorage, and reinforced concrete details.
From simple connections to complex geometry, Idea Statica helps engineers better understand real structural behavior, visualize load paths, and streamline code checks with advanced analysis and BIM integrated workflows.
It's a powerful way to move beyond simplified assumptions and get a clear picture of how the details perform.
Check out Idea Statica at the link in the show notes. Well, Max and I, we got a tour of your facility many years ago, and we both spec'd BRBs on projects. I should say buckling restrained braces. For many that maybe don't know what that is, probably the West Coast knows really well what these are, but maybe in the Midwest and stuff. But could you walk us through what a BRB is and what the system looks like?
Yeah, so a buckling restrained brace is a brace that's primarily used in areas of moderate to high seismicity, although we've done some projects in low seismicity. But the really neat, kind of the simple concept of it is that we're able to kind of decouple the two things that a brace needs to do. And so we can take one element and make it resist axial loads. And that's the core of the BRB. And we use a separate element that's this outer casing of the BRB, and it resists the buckling loads. And so, a demonstration we used to use when I was a lot younger was we had this pipe and we put this wire in it. And so if you just bent this wire, like it was like a coat hanger wire, and if you bent the wire just by itself, you could easily bend it. If you put it inside of this pipe that had a little base plate on it, and we put it on a table, and you could push down, that thing would hit the sidewall of the wire would hit the sidewall of the pipe as soon as you push down on it, and then you could not push any further. And so that kind of element within a sleeve concept that braces that inner member. And so with a BRB, what happens is the steel core that you've sized for your axial loads is inside of this casing, and then it's surrounded by usually a grout fill or something that takes up all the space between the casing and the steel core, minus a very small little gap around the steel core that allows the steel core to be non-composite and with the outer casing. So there's a very tiny, in the orders of a millimeter or 2 gap. And so when that steel core goes into tension, it will yield at Fy times the area like we'd expect. But when it goes into compression, it wants to buckle, and it really quickly runs through these very high buckling mode shapes because it's in this confined space. And that the buckling length that can be developed is so short that what happens is you just get gross section yielding on the steel core. So you now have an element that in compression yields and in tension yields. And so you get the same strength in both directions. And that's why we say the steel core element, I said just a minute ago, resists all of our axial. So you size a brace as an engineer, you get the axial component that you need in that brace. And if it's 250 kips, you divide that by phi and Fy, and you've got your core area that you need, and you're done. The buckling calculation matters kind of architecturally for this casing as far as where it's going to fit, but it's not. It's no longer kind of an engineering concern about sizing this brace for buckling or B over T ratios or anything like that. So that's what makes them very efficient. That with a traditional brace frame, you would size the brace for its buckling capacity, but the frame members all have to get designed for its tension capacity. And so there's this wild imbalance of what you gain in the brace for using up lateral forces is small. It's the compression capacity, but what the price you have to pay is the tension capacity of that brace. And with a BRB now, those two, tension and compression, are the same. And so you can economize the structure and tune it very well.
Yeah, that makes a lot of sense. When I've seen them, the gusset plates seem way smaller than a special concentric brace frame system. Where did the technology first start? Where was it kind of founded, and when, I guess?
The technology was founded in Japan at Tokyo Tech, and the company probably many people have heard of, Unbonded Brace. They did a lot of the initial research, and then was brought over to the United States in the early 2000s.
Oh.
One of the early projects was the Wallace Federal Building that was in Salt Lake City, Utah. And that's kind of where our company was founded, and we kind of learned about it back around that time. And that's why a lot of the buckling restrained brace companies exist in that Salt Lake City area. We kind of started in that area. And so early 2000s-ish was, maybe 2003 or 4 was that building. That's not true. It was probably before. That was probably 2000. CoreBrace then started researching and developing in the 2000s, or 2000, and our first project was 2001 or 2 as well. So we didn't do that Wallace Federal Building, but we started shortly after that, testing up the University of Utah, where I was at school and did a master's degree. And then the company was founded, I think, in 2001. So it will be maybe 2001, something like that. So, but yeah, that's the start of it. And it's been going strong now for 20 quarter century. What is it now? 26 years?
Yeah. So you mentioned buckling when talking about a special concentric brace frame. How should you think about the BRBF placement in special concentric brace frame or a moment frame, a high R system? How should you think about the total picture of this, and how do we choose a BRB in all the options?
Very good questions. So a minute ago, you said that the gusset plates are really big in a special concentric brace frame, and that's because in that system, that brace is dissipating energy by buckling. So yielding in tension and buckling in compression. And when it buckles in compression, those gusset plates have to be able to accommodate that buckling and themselves kind of bend and move out of plane.
Okay.
And so that's why we have to design in that 2T bend line and things like that. Now, where we think about that in terms of a special concentric brace frame or a moment frame, I think it goes without saying that brace frames are always much less expensive than moment frames. Moment frames have a great place in the world when you need that flexibility of space. And so you're, the trade-off for the prices. But when a buckling restrained brace frame can be, or a brace frame in general can be accommodated, they're going to produce a stiffer building with lower drifts and lower costs. Now, within the realm of brace frames, especially in the seismic applications, the buckling restrained brace frame is going to be the least expensive, and that's been the magic of a BRBF, and why CoreBrace has been so successful, and why buckling restrained braces have been so widely adopted, is that their performance is amazing. It's seismically, it's great performance, but also from an economic standpoint, they're very favorable. Almost always the most economical option. When I said my father was a contractor, he got into building homes. We did a lot of, I would do framing for him in the summers. And I remember going to the home show with him once, and we were looking at all these neat, products that you'd see at the home shows for insulated panels and things. I was like, Dad, we need to use this, and we need to use this. I'm in high school, and I'm taking pamphlets for everything. And he says, there's a lot of things that are economical, but don't function well. And there's a lot of things that function very well, but aren't economical. What we have to do is find the things where that overlaps, find the things that function well, that improve performance and bring economy to our building. And that's the sweet spot. And that's really what a BRB is, and why it's magic, is that we can reduce the cost and the tonnage of the structure, but increase performance. And so I would say in the realm of a Moman frame and a brace frame, that's a decision that, we make a real intently try not to tell an engineer they should use a BRBF over a Moman frame or something. These are smart people, right? And that decision is like made for, do I need that functionality or do I not, right? But if you can accommodate braces, it's in the realm of braces, it's the way to go. They're the most economical, and the performance is very beneficial to the building.
Yeah. Made me think, like, what is the capacity of the braces, the low end and kind of the high end that you guys can create, along with the length? I mean, I imagine at some point it doesn't make sense.
You are getting into a topic that all the guys in my office and folks in my office are rolling their eyes right now, because this is something I feel very passionately about. It's really, really interesting so we did some testing for a bridge project up at the University of Buffalo a couple of years ago, and Professor Bruneau said, hey, I need to get some, I don't remember what they were, 3/8 square inch braces, right? And they were like 4 feet. And I was like, 3/8 square inch, but that's. And he's like, they're 4 feet. And turns out we built those braces and sent them over, because it was a scaled down model, right? It was a scaled down model of this bridge band. And I'm going from memory what the exact size was, but they were tiny. And at 4 feet long, they worked fantastic, right? Fantastic. At 20 feet long that you'd put in a building, those would barely hold their own self-weight, right?
Yeah.
Because that piece is still 3/8 of a square inch inside of there, and it's got to be able to accommodate 2% story drift. So there's got to be a pocket in there for this to stroke in and out of that's unbraced for a 3/8 bar of steel under high loads, right? So how the sizes you can do and accommodate are, especially at the small end, are very sensitive to how long the brace is. But in general, for typical building sizes, we like to ask folks if the building can accommodate, if it's a new structure, for example, can we stay at around 60 to 80 kip brace, a 2 square inch brace?
Yeah.
We've tested smaller than that. And we have what we call a perforated core brace that and I don't mean a perforated core of the BRB, and it's a brace, so a perforated core BRB that we've tested down to, I think, 3/4 of a square inch at that 20 feet long.
Wow.
And they can work. And so their internal workings are a little more complex. So we cut a pattern out of the steel core. So instead of necking the steel core down to be, 3/8 of thickness by whatever width makes 3/4 of a square inch, instead of necking that down like a dog bone, we actually keep the plate the full width, and then we cut out a pattern. But that pattern that's cut out leaves some steel pieces in there, but there's relief cuts around them, so the steel can move around but the steel kind of relief cuts, they still brace these pieces so they can't buckle on themselves. That's a little more expensive to fabricate and the overstrength on them still, because they're flexible, is still a little bit higher. So a 1.5 or 1 3/4 square inch perforated core BRB would probably have similar overstrength to a 2 square inch BRB that's not a perfect core. So we'll say, hey, if you can stay at a 2 square inch brace on new construction, and that's not going to hurt you, that's going to be probably a little more economical brace to build. It's going to probably have lower overstrength. If you need to, for some reason, a retrofit for sure, we'll go down and do that.
Yeah.
I just looked at a structure a day or two ago with somebody that had a 1 square inch brace, but it was 9 feet long. Well, we can do those all day long, right? Those will work fantastic. On the upper end, I'm not sure if that was part of your question, but on the upper end, how big we can go, the sky's really the limit. But the reality of that is there's a qualification testing component or requirement for BRBs. So when you provide a BRB on a project, one of the things we do in our office, we have to figure out which 2 tests we're going to qualify that with. And we provide, from the results of that testing, we provide you the overstrength factors, or ultimately the maximum tension and compression capacity-based design values that you need as an engineer need to size columns and beams and frame members around, and what we design a brace around. Those 2 tests that we do that are required, one is a kind of a similarity test, and the second is what the provisions call a subassemblage test. And that subassemblage test has to have rotations in it. And the reality is we do all of our tests, virtually all of them, with those subassemblage rotations. So any of our tests can qualify for that. But there's not very many laboratories that will let you eccentrically load a member in frame actions with 2,000 kips, right? 10,000, 10 meganewton. So the limitations of the testing laboratories, we've done tests bigger than that. A 1,000 kip yield brace, will have an ultimate strength by the time you finish testing right around 2,000. Usually by the time we test them to really high strain demands, we're nearly doubling, maybe 1.8 times, right? And so there's not a whole lot of labs that have that capacity anyway, but then laboratories that will say, hey, we'll let you put a rotational demand on that. There's really not. So some laboratories, there's a laboratory in Taiwan we've tested out that can do larger forces, but they restrict you to uniaxial only. So back to your question, we could build a brace as large of capacity as you want, but you start to get outside of the testing, the ability to do that subassemblage test. We would have an axial test. The provisions allow extrapolation beyond your largest, and I should say there's extrapolation ranges for those 2 tests you have to have. And on the subassemblage test in particular, it used to have to be larger, as large or larger than the brace you're providing. Now it can be 90% that size. So you're allowed a small amount of upward extrapolation, but not a ton. And then it says you can extrapolate beyond that. The provisions say you can extrapolate beyond that if there's some justification that you have to do. We don't need to get into the specifics of that. But so what happens is when you're providing a brace larger than that on a project, you kind of open up that you could have questions from a plan reviewer or something. Whereas if you stay below that range, you're kind of just in the clear. This is 100% by the books. We don't need to do anything. So we've provided braces much larger than that testing limit. We've gone through peer reviews on many projects that had very large braces. But another option is we'll see braces gang together. So two 1,000 kip braces, or we've done 4 18 square inch braces. And so the brace itself is all individually qualified. And these are literally 4 separate braces. So they pick them up and one at a time and put the 4 in or the 2 in. So that's kind of a neat way to go and stay within a test range. But probably more projects would use a larger brace and just say, hey, we'll go through the review process and make sure, and qualify that way. But either of those is an option.
Yeah. I just to paint a picture in my head here, if you had a 2-inch square brace, is this a square or rectangular either way, continuous 2-inch all the way to the end to the brace connection, and that is in a concrete, preventing buckling?
That's a great question. So we said a minute ago about the dog bone cut, right? So that, let's say on that 2 square inch brace, you'd probably be 4 or 5 inches wide at the end, especially as it exited outside that casing. And then, you form actually starting inside the casing, the connection, so that when the core extension exits outside the casing, you have it's usually a built up, either like a cruciform shape or usually in the US, it's like a semi-8 shape as it exits outside of the casing, and you have some moment of inertia there, in plane and out of plane. And then it goes on and connects to the structure. So the core itself would widen out to probably 4 or 5 inches. It's usually in the same plane as the gusset, and then you're building these connections off of it that are going to lap onto the gusset.
Okay.
I'm thinking of pictures I've seen where they've ganged up the BRBs, outriggers on tall buildings. Was it Wilshire Grand that had the 4? Okay.
Yeah.
It looks wicked.
Wilshire Grand, that was an Impon Steel project, and I remember looking at that. That had tons of very large braces on it.
Yeah.
I'm trying to think, but 2&U in Seattle that we've done had a gang of 4 braces. Actually, and those are all exposed. You can walk up and
cool.
See a lot of those.
As it always should be.
Yeah. And we've done some gang brace on several projects in Seattle and other places, but the Philippines I can think of. But there's.
Okay. Yeah. What's usually the biggest misconception when someone's first using or trying out a design with BRBs?
I don't know if I know what the biggest misconception is, but I think just offhand I would say that maybe back to what we said earlier, that, hey, I'm getting something that's higher performance, and so therefore it's going to cost more.
Yeah. I believe that.
Viscous dampers are a really neat technology, and so I think there's and they're going to cost more, for example.
Yeah.
And I think maybe sometimes people think a similar thing about a buckling or strain brace is that, hey, this is a really neat technology, but it's going to cost more. But I think maybe equally misunderstood is it's going to have more complications to design. And that's really untrue. In fact, we said earlier, like, you as a designer, as the structural engineer, you're finding the axial demand in that brace and dividing by a phi factor. And 3.24 inches, I'm going to use a 3 1/4 square inch brace and specify that in the software, and you're done.
Yeah.
And back to that question about the core tapering out, the end result of that is that brace axially is a little bit stiffer. And so you've got to apply that stiffness modifier to the element, and most softwares will just do that automatically for you and determine the area. And that's done. The gussets don't buckle like we talked about a minute ago. You don't have to calculate any elliptical bend line or 2T bend lines. The gussets are small and compact, virtually always deferred to the BRB manufacturer to design those. So really, in the end, it takes a lot of effort off of the engineer of record to do a BRB. The design itself is simpler, and then you're deferring the connections almost all the time to the BRB manufacturer. So probably those two things are the biggest misconceptions. And then I would add, that the coordination maybe that's done with the manufacturer might be something that people that haven't done it before are a little worried about. But BRB plugins exist included with eTabs and RAM and RISA. There's design guides for other softwares as well, if you need. But in those softwares, there's an element and you just put it in, and it automatically runs. And actually, there's other softwares I know in the works right now that are actively putting those in. So you design that, and then any coordination you do want to do, usually those softwares are kind of making an approximation of, say, that stiffness factor, and certainly the overstrength factors. They're making an approximation of it. So most designers and engineers, before they go to the bank and really, I'm going to start specifying things and start letting things get bid out, most of them will reach out to us and say, hey, will you just look at this model and make sure that, tell me anything you'd modify, so that when I do, as the engineer, specify these on my drawings, I'm specifying something that can be built. I don't have to come back and check a different value that's really what can be built.
Yeah.
And that's something that's provided for free, and there's no obligations, and we don't make you sign any contracts or anything. And so that coordination might be, I guess, one other thing that's a little misconception.
Yeah.
This episode is sponsored by Idea Statica, software built for structural engineers designing steel connections, anchorage, and reinforced concrete details.
From simple connections to complex geometry, Idea Statica helps engineers better understand real structural behavior, visualize load paths, and streamline code checks with advanced analysis and BIM integrated workflows.
It's a powerful way to move beyond simplified assumptions and get a clear picture of how the details perform.
Check out Idea Statica at the link in the show notes.
When someone's working with a BRB supplier, are we saying we need this grade of steel and this area, or do we just give the force that is required? And also actually on that, what levels of steel area can we look at? Obviously, we can't get down to the 32nd of an inch, but there is a scale here. What does that look like?
That's so funny. We had Zach in our office did a program when he was in college, senior design project, I think it was, and they did all their design and came up with this little tiny 1/32 square inch BRB. I don't remember the number, but we all laugh about it now because it's such a small thing. The grade of steel, which usually used for buckling or restrained brace, I kind of always joke that we might be the largest purchaser of A36 steel left on the planet. We predominantly, like 99% of the braces that are fabricated or more, literally 99.9 are made of A36 steel. And the reason for that is because with grade 36 steel, we get a little bit more area for a given load.
Mm-hmm.
And that gives us a little bit more stiffness. So for resisting the same force, we can be a little stiffer. But it's also got the difference between yield and ultimate is a little higher. So there's more ductility built into that steel. We have done and we have tested braces of other grades of steel. We've tested braces of stainless steel even, but we tested a number of grade 50 steel. But the A36 steel is a really nice spot for ductility and stiffness. So now, do you specify a force or an area? That is an option that the designer can pick. It's almost always done as an area, though.
Okay.
And what we usually do, so without getting too deep into this, but when we specify in the seismic world, when we specify something, it's sometimes conservative to specify on the lower bound of the expected strength. It's oftentimes conservative. And that's usually what we think about. Hey, I'll assume this A36 steel is 36 KSI. And so, but sometimes in the seismic world, it's unconservative to assume it's going to be at that pumping. When we talk about designing the frame for the capacity of the brace, it would be unconservative to assume that it's 36 KSI.
Yeah.
If it's really going to come in at 45 KSI. We've under-designed our connections. And so this RY factor that's in the seismic provision is what accounts for that material variability. So at times when you see RY applied in the seismic provisions, it's saying, hey, the conservative thing here to do is to use the upper bound. What a BRB does, what the BRB industry has done, is that we tighten up that range of 36 times RY is 1.3 times that number's up at, around 48 or something. But what the BRB industry has done is we've tightened that range and said, we know statistically and from the mills that we purchase from, we can control the chemistry of the plate and ensure that we have this range of 38 to 46. So that's about a 1.2 factor instead of 1.3. So new construction will generally say, I'm going to size the brace on the bottom end of that range, 38 KSI, and I'm going to check my capacity base when CoreBrace provides the engineer back these adjusted brace strengths, tension and compression, the ultimate, capacity-based tension and compression to check the frame members. That's going to be based usually on 46. Another option that would be akin to what you're saying about specifying the force. You could specify. You could say, I want a 250 kip brace. But as the engineer, you have got to somehow tell your software what that member is. And you tell your software what that member is by converting it to an area and then applying a stiffness factor to it.
Right.
And so you're tracking that number in your software. And then if you convert that to 250 kits to put on your drawings, send that over to the BRB manufacturer, they're going to convert it back to an area because they can figure out something they've got to build, right?
Yeah.
What's the moment of inertia of it? What's the width of the core need to be? We need to know all those things to do our design as well. And so what becomes easier, even in this, what would be called a force-based design, where you're wanting to use a 200 kit brace and you 250 kit, whatever you're saying, and want to maybe try and remove that 1.2 material variability, is that you would pick maybe the middle of that bell curve of expected strengths between 38 and 46. You would pick 42 KSI. In your software that you're designing with, you would set 42 KSI as the FY of that BRB material. And then you would just specify a brace on 42 KSI. That came out to be, 3.5 square inches. You specify 3.5 square inches. And then you would have some language in your drawings that says, this is 3.5, or these specified areas are based on the assumed 42 KSI, and the manufacturer will resize the brace based on the actual strength of the material at the time of manufacture. So I should have said in the first option, whereas the engineer, you're sizing on 38 and checking capacity of 46, you would have a note in your drawings that says, the manufacturer, when you fabricate the BRB, you need to ensure that you need to test the steel and ensure that it's within that range. It's kind of quite similar to doing your design for concrete around and assume 5,000 PSI concrete. You then specify 5,000 PSI concrete, and you just make sure that when it gets built, they have to ensure that it's 5,000 PSI concrete.
Yeah.
We're having to ensure that it's 5,000 PSI concrete, but not more than 7,000 PSI. But for steel. And that's a lot, that's very doable for steel.
Mm.
So that's what we're doing. In the other option, where you're assuming the middle of the range, instead of that note that says ensure that it's in that range, you're saying ensure that it's in that range and resize the core based on that. So to answer your question, either option and specifying an area based on a range, so that's what's done most often. You could specify a force, and that got done more in the past, but the industry's largely moved away from that. Important in all of these is we have to account for the material variability. It exists no matter what. We can't say 42 KSI and I'm going to make no way to accommodate the actual strength of the material. There's always has to be a plan how to accommodate within that range that we know we can get.
Okay. The increments of sizes. How many past the decimal point? How far can you carry this?
Yeah, great question. So theoretically, you cut to any you want, and so we can, for bookkeeping purposes. And if you look in softwares, these softwares that have this implementation, usually there's something like a 1/4 square inch increment.
Okay.
And then again, usually when you get up, say 10 square inches, you're going to 1/2 square inch increments or 1 square inch increments. And usually that's done to kind of keep the rounding error 10% or less. Many engineers will use 1/4 square inch increments all the way through 20 or 30 square inches, and there's nothing wrong with that. But a 1/4 square inch or 1/2 square inch is a nice kind of even number to be able to just track on your drawings and leave a little bit of room if some tiny angle change happens. You could go in and specify a 3.2 square inch brace, and we will build it. As long as you understand, there, especially down at really small braces, the cutting tolerances and the fabrication tolerance are, probably a 16th of an inch or something on cutting that width. And so you probably don't want to get too precise, but specifying, something to a 1/10 of a square inch is probably, don't see it a ton. It's probably not, unreasonable if you're trying to really, I guess we want to be realistic about, if you really need that much
precision, yes.
for your, column fails, whatever. But in a retrofit, for example, a retrofit of a structure where you're trying to make an existing structure work, that's especially where we would do this option of assuming the middle of the bell curve and resizing around that, removing all of that overstrength. And we'll see a 5.8 square inch brace specified there.
Yeah.
But even then, I think a lot of times people will say, let's stay at a quarter square inch. And again, if you need that level of precision, you probably need to be pretty confident that you're going to be able to get that. So that's something we're happy to, talk about on a project by project basis of like really how tightly can we specify this.
Is there a detriment to having a core that's bigger than you need from a system standpoint and performance? I mean, let's say you have a brace at the roof you need and it only needs to take 20 kips, but you can only order a 60 kip brace. How does that affect the designers?
Putting in any seismic fuse that's bigger than you need kind of is the same as reducing your R factor a little bit.
Yeah.
And so you will you'll absorb more seismic force before the element starts to yield and dissipate energy. So the short of it is that you'll have higher demands in columns that you need to design those columns. How detrimental that is when you're talking a 2 square inch brace. Again, that usually, we said earlier, if your structure can accommodate a 2 square inch brace, we recommend not using that as a minimum size. And most of the time, structures can accommodate that small brace and handle that electrical strain. The gravity loads or other things that you need to have, needing practice, will usually make it so that you can accommodate that. We do see it, the penthouse structures, people oftentimes will want that smaller brace, and that's where we will go into smaller brace. If, we see most buildings, schools, the 1 or 2 story buildings, generally, it doesn't take a very large building to need a brace bigger than 2 squares. But if you do use, there are actually sometimes advantages to using a brace that's a little bit larger, and you'll have probably better residual drift performance and things like that. So,
is there like an acceptable range that people, if they were like, hey, I need a 3 square inch, hypothetically, and you said we can only do 3.25, is that like an acceptable range where it might be a little bit bigger than their system? They're accounting for. They iterate their system design with that new size.
Yeah, usually that's
okay.
I mean, frankly, what usually happens is the engineer is working in their software platform, and the sizes that are kind of pre-programmed in there.
Yeah,
we needed to make some kind of meaningful delineation of sizes. So it's like that quarter square inch, and then I think it bumps up to a half square inch, and then probably to 1 square inch maybe at some point in the software. And so usually someone's just picking the closest size. I mean, that's kind of akin to saying, hey, the next bump in column size up is X.
Yeah.
And then probably usually a smaller bump than that. And so braces, when you see, many of these studies that have been presented even here at this conference, the demand capacity ratio on a BRB is usually targeted, 85 to 0.85 to 1.
Okay.
And I don't think people even give that a second thought. If you did need something between a 3 and a 3.25, we'd be happy to build that for you. But it's really below the smallest end is usually where that gets in. But you're right. I think the extension of your question would be like, let's say we take a copy exact building and we move it from San Jose, California to Phoenix, Arizona. Copy exact. And now you've got braces that are much larger than you need down. That's probably would require some more thought and want to think of, do we want to downsize those braces? Because now we're going to, maybe never yield the building. But in either case, you're going to build up strength in that brace. And columns also stay the same size in a copy exact building. Presumably the building will stay elastic for a longer period of time before it started dissipating energy. But we do see that. That's probably where I see your question becoming a design consideration more often is, hey, we're doing this copy exact and for a whatever type facility, manufacturing facility, and we've moved it to an area of lower seismicity. What do we need to think about in now the demand that's in our braces?
Yeah, that makes a lot of sense.
I heard you mention the word retrofit. Are BRBs effective in a retrofit of a system? And then is there anything that an engineer needs to consider in a retrofit that they might not have to do in a different system?
every engineer has ever done a retrofit right now is like, there are so many things you have to consider. The BRBs are fantastic in retrofits, and that's a very meaningful percentage of the use of BRBs. It's by far not the new constructions that are the most meaningful, but many retrofit projects use BRBs for the reason we just talked about, that ability to customize and really tune, maybe even to an extreme, tune the strength of the brace. And so in a retrofit, you're taking something where the existing lateral system is insufficient for whatever reason, and let's say the lateral system isn't strong enough for now what we know the seismic demand to be, or we're adding on the building and increasing the seismic demand, and so but we want to keep as much of the existing structure as we can. So if I could take something like an SCBF that, hey, we sized the braces for this lower force, but we sized all the frame for this upper force, some of that residual capacity that's there, I could put a BRB in that's stronger than the existing braces, but if it had less overstrength than the existing braces, a lot of the existing framing might be able to be reused. And so we see, because they can be tuned to the force levels you need, and the overstrength on them is so well understood, they're a great option for retrofits to get used. Yeah, time and time again. I mean, many times we've seen at any given time, we've always got a number of our projects that are in the works, our retrofit projects.
That makes sense. Yeah, I've personally put them in existing buildings, and it is very convenient. And using the existing framing, I like that. What about technology-wise? It seems in my career, BRBs appear to look the same and things like that. But I went to this conference that had timber in the name, and I saw a BRB that was cased with, I'd say, glulam or something similar to that. What is the future and the new technologies research that's being done?
So one of the things that we've recently developed is this perforated core that I mentioned. That's something that's probably changed, or certainly it's changed over mine. We've looked at building, not looked at, we've done a lot of research and testing and provide them now BRBs that are built with multiple plies in the core. And the idea there is, if we can avoid using a core that's made out of 2.5-inch thick material and make it out of 2 plies that are 1.25-inch thick, instead, you can use a plate that through its thickness has more uniformity. You don't get some of those through the thickness issues where you're maybe not consistent to that. And so we really like that idea of using these. You have to do a Sharpie test, for example, on thicker plates. Well, if we can, and we certainly would do the Sharpie test, but if we can stay with thinner plates that are going to have better ductility, we're actually testing down at UC San Diego right now, some additional testing on that, trying to expand our understanding of that. What would happen, for example, if those 2 plies were very different material strength? We never do that. We always build the exact same plate. But what would happen if we did that? And how would that compare to a baseline case where they're built out of the same plate? We're always doing research. One of the topics that was presented to yesterday, I believe it was BRBs used in an eccentric configuration. Oh yeah. So that's one of the things that's going through the seismic provisions right now. There's a provision in there now that says you can have these small eccentricities as long as the source of inelastic deformations remains the BRBs. So you can't have a link, an EBF type link, even though there'd be a space between those braces. That beam has to remain elastic. But it allows you to have some small eccentricities if you design it a cap core. And so the idea on the seismic committee was, well, if I have to design around it anyways, why I don't want to say arbitrary limit, but why a limit if I have to check the limit states anyways? Why a limit of 1 times the beam depth? If I need to go 1.5 times the beam depth and I've designed around that, why not? Granted, my beam's going to be heavier.
Right.
So we've done a bunch of research on that, and it was presented, like I said, yesterday by Paul Richards and Chao-Shin Lee, who's with us. Paul Richards is at Brigham Young University. We presented research on the effects of changing that eccentricity and methods for designing the beams and the columns to accommodate those eccentricities. So that's one thing that's changed. And that's one thing I think that potentially in the future you might see used a lot more often, because architecturally that gives you some advantages to be able to get maybe that freedom of space or approach towards that freedom of space that you would get more with a moment frame or certainly with an EBF, but still keep the stiffness and the economy of a BRB. One of the findings that they found in that actually was if there was one of the configurations where you arrange it as a single diagonal, but with an eccentricity, like if you're going to have a door right next to a column.
Yeah.
And so you pull the brace out. Usually that's the only reason we're doing these eccentricities, to accommodate a door, a corridor, or a window or something. But if you pull that out a little bit and then you have this little stub off of the column, and that in our analysis was moment connected. And it turned out that kind of half moment frame performed a little bit like almost like a little strongback system and provided a great restoring force to the structure that actually reduced the residual drift, and there was no real appreciable increase in the frame weight, total weight, because of that. Now the connection be slightly more involved, so I'm not going to suggest, but performance-wise, it was really good. And I think that's something people will maybe think about a little bit. That's an interesting idea, but certainly just in general, hey, we can now accommodate larger openings, and we know how to size them, and importantly, in the next version of the seismic provisions, it will now be allowed to go a little bigger. So that's another bit of research we're working on, or that we just finished up, I guess I should say.
That's pretty cool. So we did an episode recently with Tipping on their mass frame, one of their mass frame projects that used BRBs. What other unique cases come to your desk that you're like, we've never thought of this? New things. This. I know when we talked last time, maybe bridges or something but what unique cases are people come to you with?
Yeah, bridges is a unique one. We've done a handful of bridges probably since then. I've seen some very interesting. We talked about outriggers before within a structure, but we've seen some structures where it retrofit in particular, where they're maybe put on as like external buttresses.
Oh,
and so a building where maybe you can't get inside. And so there's one in particular that I can think of where a concrete buttress was built outside of the building, and then between this concrete buttress and the building, horizontally up at the diaphragm level, a BRB was attached.
Wow.
As a building, and every 20 feet or so along the length of that there. But we've also we've done a really cool project down China Basin that put external buttress frames on the structure. Really, really cool looking. And that's been used in a similar concept been used, or maybe there's a buttress even just down at the ground level on the outside of the building, and then two diagonal braces attaching up the second to the top of the first floor diaphragm and the roof diaphragm angling down. That's an interesting one that we've seen. Let's think for a minute.
What's the stainless steel core for a bridge?
The stainless steel core was for a bridge. This could be a whole other topic. This is, I think, a really interesting thing. The demands that were on, this was the Vincent Thomas Bridge, was what the testing of the stainless steel core was done for. The Vincent Thomas Bridge has a fault. It's down at the Port of Los Angeles, and the fault line runs right under that bridge. And so it's a long span bridge. There's probably plenty of people that have driven this bridge, but so the demands on that were pretty high. And so they were doing a retrofit of that bridge, and they were adding in these BRBs. And so this was 2012, I think, when we did that testing. They came in and they said, hey, we need this BRB to resist this very large near fault 4.5% strain. And at the time, understanding of that was how to accommodate those strains. If you've done an AISC test and if you can get to 3.5%, you've done fantastic. So how do we get to 4.5%? And so stainless steel became an option, but we did also test mild steel braces in that, our regular braces. And I think I said earlier that the core is oriented perpendicular to the gusset. But back then we used to orient these cores parallel to the gusset. So I said that backwards earlier. But back then, that's how we did do it. And so the stainless steel brace was made that way. And the downside of that was it kind of forces the gusset to be the same thickness as the core plate. But anyway, so we tested both those materials, and the stainless steel generated so much overstrength that it actually overpowered the system. It would the overstrength that it generates was really difficult to handle. But the long and short of the story, why I'm telling you all this is that a near fault pulse of 4.5% strain in the brace is not the same as a cyclic test that goes to 4.5% strain, that goes to negative 4.5 and positive 4.5. And so we actually were able to accommodate with the mild steel brace even very easy, in fact, better than the stainless steel brace, this 4.5% strain. And the end of that story is we provided, I believe, galvanized mild steel braces. We did a couple more rounds of testing and refined that brace even further, ended up providing not a brace that had the core parallel to the gusset and all of that. It's a more modern design, and it was galvanized fully through the core instead of the stainless steel brace. So to my knowledge, I don't believe we've built a fair number of them for this testing, and I say a fair number, but 4 or 5 or something. I don't believe we've ever provided a stainless steel brace. And I would be very careful. I would think a structure that wanted to use a stainless steel brace with the testing that's available on them now probably would still want to do some project-specific testing and make sure. Joel Lanning's done some good research on that, trying to quantify the overstrength that's generated from stainless steel. But there's really only, I think, those 4 braces that have been tested, and they weren't tested. I believe we did probably one AISE type test in that, but it was after the site-specific test, so there's probably already some strain hardening in that.
Yeah.
And so it's probably hard to understand the stainless steel performance. But anyways, back, we've seen a lot of cool mass timber structures. We did a retrofit of a big mass timber, really old mass timber hangar that got steel multi-tier brace frames put in as the retrofit.
Oh, that's cool.
It was a really nice project.
Saw those photos, looked really amazing.
And we're, engineers are always coming up with fantastic, amazing things. And I'm probably not doing it credit of all the things I can think about on the spot, but there's amazing, interesting, non-conventional uses of BRBs all of the time that we get to see.
Yeah. Well, as we wrap up here, what question have we not asked that you think people would have value to hear?
In the new technology and what we're doing, I probably should have, mentioned this stuff that we've worked on with resiliency and functional recovery, and coupled with that, the post-earthquake assessment of BRB. So one of the other research things we've spent a lot of time on is developing a fatigue life model for BRBs. That allows us to calculate, if we know the displacement history of the BRB, how much of its life's been used up.
Wow.
And we've written a very neat paper that was based on, I think now it's upwards of 20 full-scale BRB tests establishing the fatigue life of a BRB. And so you could, for example, now take a nonlinear response history model. Back when we did that Vincent Thomas Bridge, if we had known this, we could have run their anticipated protocol through this fatigue life model and said, our mild steel make that easy. We could do that 2 or 3 times. We didn't know that back then. We can know that now. Running a nonlinear time history model now, you can use this fatigue life model to as one means to check and qualify your brace. In fact, if you were doing a nonlinear response history model on that bridge and you came up with a 4% strain, you would have said, there's no test in the world that says that will work. But the flip side of that is we've done test to earthquake protocols numerous times, including on that bridge, that show it works just fine.
Yeah.
But there may not be. So this allows either for in the design phase to do a check or after an earthquake to do a check. And we have a device you can put on the brace if the owner wants it, that kind of sits there and sleeps. And when an earthquake happens, it turns on and it records the motion and it turns off at the end of the earthquake. We call it a recorder. And I think we spelled it wrong. So the CORE in the middle on N10, that's a little mark. The recorder. And then at the end of the earthquake, you can just pull the little SD card out of that or download it, however, plug it in and run it through this fatigue model. And you can write a letter to the owner that says, hey, you've used 10% of the brace's life. You're fine to leave it in.
Wow.
The flip side to that, now we've looked at fatigue, and all of the testing that we've done has shown BRBs will go through 10 earthquakes before they're fractured. We did one, no joke, 3 days ago. We're testing for a project that we're doing in Turkey, and we did a 4 earthquake run that went to actually about 4.5% strain, and it went through 5 of those 4 earthquake runs. So 20 earthquake before.
Wow.
So quantitatively, a BRB is going to survive an earthquake. Qualitatively, if you need to be able to write a letter to an owner, this fatigue model is nice for that. But the flip side to that is if my building, younger Brandt, when I was younger, people would always say, hey, BRBs are great, right? Because I can just take it out after an earthquake and put a new one in. And while that's true, the reality is that BRB can survive 20 earthquakes, like we just said, right? So you shouldn't need to take it out. But if the building's got a 1% residual drift, is not going to be usable, right?
Yeah.
Like what happened down in Christchurch, all the buildings get torn down because they were leaning over too far, not because they collapsed. Then it doesn't matter if I can take that BRB out or not, right? So we've also done a lot of research with, we have resiliency design aids. We're part of the functional recovery task group at ASCE 7 or in that SP3 software, saying if you want to intentionally design a BRB, a BRBF, your building to have functional recovery, to be usable after the earthquake, here's how we can do that. To know how, we talked just a second ago about that single diagonal with eccentricity, how it limited the residual drift, right? That's probably not the preferable way to limit residual drift if you didn't need a door opening right there. But there are many other ways with the BRBF building too that we now know and can quantify. How do I limit the residual drift that my building's going to see so that I can have a building after the earthquake that is reusable? So I think those are two sides of the same coin of being able to say, I know that the BRB is going to still have fatigue life left after and not need to be replaced. My building will still have strength after the earthquake, but also that my building will still be in a usable state after the earthquake. And I think that's a very important thing. Again, all of these things we could do a podcast series on these, but they're all fascinating topics, but at least a little, takeaway of if you're thinking about that and you're using designing a building and you need to try and ensure that it's going to be usable after an earthquake. It's more to me than saying a lot of times the catchphrase is, oh, this can just be replaced after an earthquake.
Yeah.
A, you don't want to try and get a contractor in there to replace it. But B, especially with the BRB, and I think maybe with a lot of these other systems, if it survived, if after the earthquake, the BRB for sure has got residual life, right? I mean, my lawyers out there, I'm not going to say for sure, but everything we've seen says a BRB is going to have ability to survive certainly design level earthquakes, multiple, but MCE level earthquakes, even these earthquakes we just did, they're at MCE level. They should be able to survive multiple earthquakes. And so it's not I can just replace this really easy. That's the solution to my problem. It does not matter if it's like, hey, you can replace that window, but the building's leaning over so far. And you can't get the new window back in that space because it's a parallelogram now.
Right.
What does that matter?
Yeah.
Right? You need to keep that window opening square. And if you kept it square, the window's probably not going to be broken. That's how it is kind of for the BRB, right? We want to keep it in a state that means we don't have to do repair, and the BRB is not going to be broken anyway. So,
yeah.
anyways, yeah.
Awesome. Well, Brandt, thank you so much for joining Max and I on the podcast. It's been really fun. We joined one of your talks this week, and I know I learned a lot about multi-tiered BRBs. And then we walked around town and saw multi-tiered brace frames. So that was pretty cool. But
I saw some being erected right over here.
Yeah. Max and I maybe walked onto the job site. We'll just leave that one alone. But
cut that out of it.
But yeah, thank you so much for your time.
Okay. Thank
Appreciate
you.
it.
Thanks for having me. It's great. This is fun to meet up at the conference. We'll do it again next year or something.
Yeah. Perfect.